it's incapable of dealing with the real world. So if you want something that deals with the real world environment with all its complexity, why not look to something such as a blue sky? Something such as this cockroach here that's able to navigate up this flight of stairs made from lucite blocks whose thickness is much greater than the body height of the organism. Yeah, we had a little problem with the video. You can see with its 6 legs, it's easily navigating up this basically complex terrain. Actually, you can make the lucite blocks even higher, maybe twice the body height of the organism, and it's still able to climb up and over them. And usually this is done very, very quickly. They're pretty impressive to watch, except when you're in your house. But okay, there's an example of something that's able to deal, what we can term a simple organism that's able to deal with a really complex environment. So there's a shift basically to look to biology for inspiration. And if forced to pick like a focal point for this, I'd have to say it was Rodney Brooks' Assumption and Architecture Ideas. And he has a quote here which basically reflects what seems to be an obvious statement, his inspiration, that it is instructive to reflect on the way in which Earth-based biological evolution spent its time. So not only is this saying that look to biology basically for things that do what we want, to solve these technical problems that we want to solve also, but in addition, that this focus that Eldon was talking about with GOFI on higher cognitive processes actually occurred much later on in evolutionary terms and much more quickly. So what we thought as the simple problems, such as navigating a room or basically finding a mate, those things took much longer and are actually very complex tasks in their own right. So for this, an example here, I guess this change in idea. Is yours brighter? Thanks. Okay, the traditional approach basically with this linear processing, in which there's basically a large disconnect between sensory information, this linear progression, all the way to the motor output. Whereas his approach basically has this behavioral modules, in which there's a short connection between sensory information and the actuators, and that these different behaviors do different things. It's a lot more robust. Right. So from this basically paradigm shift to biological inspiration, there was a whole plethora of techniques, design practices, and tools that came about, or even if they were previously worked on, then they were a lot more focused on, became a lot more popular and studied, such as GAs, genetic algorithms, artificial neural networks, the ideas of embodiment and situatedness, and I'll explain each of these more in detail, changes in robot design, the hierarchy of simple behaviors, and then neuromorphic engineering. And we'll just take a little walk through each of these. So for genetic algorithms created by John Holland, back in the 60s, I believe, he basically took 2 mechanisms of modern evolutionary theory. Genetics on one hand here, and natural selection on the other. From genetics, we get the idea of basically heritable variation, in which parents are able to pass on some of their genetic material to the offspring. Okay. Then from a natural selective processes, basically you get differential reproduction, in which some organisms have offspring and some don't. This can be fitness related or even just genetic, something like genetic drift, and we're just a random event. Takes them out of the population. So with artificial neural networks by Warren McCulloch and Walter Pitts, these were created much earlier, back in the 40s, but it's continues to be an active research area, and the models have grown in complexity and focused on different tasks. Their original model basically was from the 1940s neurobiology, in which neurons were thought of as basically just on or off, very, a summation basically of this input. It's very, very simple. In which you have inputs with connection strengths. They get summed, and once the summation passes some threshold, then the state of the output is 1. The summation doesn't pass thresholds, it's 0. And again, nowadays you see compartmental models which actually take into account the biophysics of actual cells, and pretty impressive. Okay, so the idea of embodiment and situatedness, these 2 ideas are represented here with ideas from our own advisor Randy Beer's work, in which if you want complex adaptive behavior, the nervous system resides not by itself, not just removed from anything, but actually within a body. that has, physical parameters to that. And then in situatedness, the body is actually interacting in an environment to move and actually produce the behavior. And this idea of changes in robotic form, there's been a huge push for biologically inspired robotics. This is Roger Quinn at Case, who has the Biologically Inspired Robotics Lab, and this is one of his robots, R3, which is very strongly based on cockroach that we saw earlier, blabbers. This basically, it's a scale up, leg length, and all these things are based solely on the cockroach. The number of degrees of freedom for each of the limbs is based on what you would find in the animal itself. And let me see if this video works. So this video will show actual posture control of the robot. It's just standing there. Its muscles are basically McKibben pneumatics, and so you'll see the guy who built it basically shoving the robot from all different directions, and watch it stay. So you can think of this posture control as one of those behavioral modules, just staying upright. He has another video on the website of which he's actually lifting up the legs, and it's able to shift its body, center of gravity over and remain stable. It's really impressive. Okay, and then kind of building on this hierarchy of simple behaviors, taking like the posture control that we saw earlier, you might have something at a lower level of just even finding a foothold. Okay, and this is Jim and Ding's work at University of Illinois at Urbana-Champaign, and so I'm going to show 6 snapshots of his little insect leg, basically finding this pin as a foothold. It's 2 servo motors, brings the leg down, and this is going to bring it down into the bar here. Okay, makes contact with it here, but it's farther up on the limb instead of being at its foot. Starts sliding the leg up, and then finally when 5 and 6 makes contact with it and is able to make that a firm foothold. Okay, so I have a video of actually that's showing it's really grainy, but it does a nice job of just this 2 degree of freedom leg that's actually able to find this little bar as a foothold. You'll see it make different contacts from forward and then swinging the leg forward or swinging it back. Actually, they'll move the foothold and you'll see it regain it. And this is all basically done by local reflexes, instead of having this go all the way up to higher processing centers and taking time. And again, the foothold is right here. See, it's made contact, regains, whoops, slipped, comes back up, situated, slipped again. And another leg strike, up, and on it. Again, this is all basically, if you have local reflexes controlling this behavior, then you don't have to spend all this processing time to send it up to higher areas. Okay, and our last example of some of these tools is this neuromorphic engineering. This is Timur Horyuch's, a lot of it's Timur Horyuch's work at University of Maryland. He came and gave a talk at Case recently. I had the pleasure of talking with him. It was pretty exciting work. So what he's done is basically created neural models through basically, VLSI technology. Well, created the chips then basically for these. That model then, his system is going to be echolocation in bats. And so he's created chips, or basically, these VLSI chips that mimic a lot of the neural dynamics in the nervous system for echolocation. And I'll talk a little bit more about his work later on. Okay. And Eldon's basically going to show these techniques that I talked about and give some examples of how they'd apply to technological problems.
Okay, so I'm going to start with talking about my master's project, which is, to be honest, probably the least exciting of the applications that I'll talk about, but this is the one I really know how it's done. I'm also expecting some hassle about this later, because what I made was a product that is useful to people who send junk mail. Basically, I was an intern at HP, and they'd just bought up this company that do one-off prints at the quality of professional print runs, but at the cost to start up of a laser printer. So, on the application, there's people who are sending out any kind of mail shot, if it's a newsletter or advertising, whatever. they may well have enough information about people it's going to know that, household A is only going to read pages 3 and 4 of this, or only going to look at these 3 items. And now there's the hardware that can actually generate these one-off prints and do personalized mailings. Depending on how you want to look at it, I kept telling myself that what I'm allowing them to do is save a lot of paper. The other side is I'm making it cheaper for them to send this kind of nuisance stuff out. But the problem is that if you just have, let's say, 7 boxes, say each of these is an advert for a product, and you just throw them onto a page, you get something like this. It's not necessarily going to look very good. So the problem is, how do you go to a layout that looks neater without spending lots of time and money with human designers who will do the job well, but remove the whole economic benefit? And the answer that I found was to use a genetic algorithm. So basically we have a population of strings, each string being a representation of some kind of layout for the given document. And you go through generation after generation, mutating descendants, and then comparing them all in some way that can be objectively measured. So in this case, what we actually did was selected the ones that wasted the least space. The rationale being that it's pretty hard to codify what is a pretty design. But if you take this and then add some space evenly, it will at least look tidy on the screen, whereas this is something of a mess. And the big issue with this kind of thing is that it can be approached as a search problem. A genetic algorithm for something that's in a restricted domain like this is basically a search algorithm. So the question is, why not just do a dumb search? And the answer is this figure, which is from the thesis, and it got me some interesting comments, because it's a log scale, and about 3/4 of the way up you reach the number of atoms in the known universe. And what's actually on it is, as you increase the number of things to be placed, the green line is the total space of things you would have to search if you just wanted to search the blindly. And the red crosses are the number of cycles that the GA has to go through. So you see, for very small amounts of data, it doesn't really matter. But as you go up, it becomes slower and slower, and eventually just outright impossible to do this as a search. And that's why things like genetic algorithms are useful, even in things that don't look like biological evolutionary problems at all. It can be a very efficient search technique. And before I leave this problem behind, I want to point out that it is of more general use than I've made it look so far. It's basically a problem of fitting items into a finite space. They're called bin packing problems as a class. And a couple of other practical uses are laying out a CPU. For one thing, you want to use less silicon so you can fit more chips onto one wafer. For another, the closer the elements are to each other, the more reliable that device will be. Another is packing physical containers. This particular example is a little easier because they are regular things. But let's say you're packing a whole range of different shape, different size objects. So the argument that at least I made in the thesis, and seems to have been well received, is that if you have this technique for doing a document layout, you can generalize it to all these other related problems and pick it up. And that's another important point about the way we work, because on the one hand, having thrown out this sort of flowchart or search idea and said, well, you can't just use the same hammer for every task. At the same time, we're not in a world where we have an unlimited number of different techniques and no clue how to use them. You can very often look at an existing task and say, okay, a similar task to what I'm trying to do has been well solved using this technique. Let's see if I can adapt what they did. Now, an example that I'm particularly fond of for the use of these techniques are the rovers that are up on Mars right now. And they've been in the news this week. I don't know if you heard, but they've actually had their missions extended by another year or so. So they've already run for, I think, a year longer than they were predicted to, and they're keeping on going. But the basic problem is that we have spy vehicles on Mars. I don't know how many of you are in Richard Thiem's talk when he's